Hello everyone. Today we will be talking about the attention which is used, and we will see some applications of it, like how we need attention in image captioning or for translating or summarizing text and so on. And then we will have a look at the transformers. Uh, we will also look at the implementation of transformers in PyTorch. So RNN, so in our last session, we talked about recurrent neural networks. And generally, RNN is used when we have to handle certain sequence problems, like, for example, neural machine translation. So in this, given a sentence in one language, the target is to, or the goal is to translate it into some other language. Here, for example, the sentence in English is being translated to sentence in Hindi. So this is known as neural machine translation. The other possibility, the other problems in which we generally use RNN is image captioning. In image captioning, given an image, we want to summarize it, like what is the action that is happening in this image. So for example, in this image, there is a woman who is playing with frisbee in the park. So we expect the network to summarize the image or the caption the image with the corresponding action, and this is where the RNN will be playing a role. So why we need RNN? Because of the sequential nature of the output and the input. Here example, India got its independence from the British. So if you look at the sentence, there is a sequential relation between the inputs, right? For example, this word got is the verb which is connecting the which is showing the action here, the independence, right? So India got its independence from the British. So these words in the sentence are related and are dependent on one another to give the meaning to the sentence, right? So because of the sequential nature of the inputs, similarly, here we have the sequential nature of the output, right? So to capture the sequential aspect, we generally use RNNs, right? And these two examples show two applications of RNNs. However, when we use RNN to solve such tasks, there are certain challenges which are being faced. For example, consider this stanza, right? This is a long description of some, so this is like a long text, like after meeting a comrade at the last post station, and so on, it goes on. And now the question is how to, sorry, how to handle this entire information at once. Suppose there is a question answering round after this paragraph, okay? So we expect the model to remember each and every possible facts there. And this is a lot of information. And now this is only 4 lines, but maybe there is a pages of documents which will be given as an input to the network, and the network is supposed to predict some output, answer certain questions, or maybe summarize it. So in both the cases, the model is expected to memorize the important parts of this paragraph and ignore the irrelevant facts or less important points. So this is known as information bottleneck. Because we have a lot of information to capture. However, our model may not be having sufficient, may not be able to capture that much of information. The other challenge we generally face is reproducing words. So for example, in this translation from English to German, the word to reach will be appearing in the German sentence in the end, right? So there is a long-term dependence as well. The words which appeared earlier in the sentence will now be supposed to be predicted at the end. And if the sentence is too long, then we want to, then this can be an issue, right? Because we are expecting the model to understand these long-term dependencies and to reproduce them at the right point. So with these challenges, what can be the solution? The solution is that, suppose if in this paragraph, right, when we have to summarize this paragraph, we want to remember some important facts, and we want to for now suppress the facts which are not very much important, right? So maybe we will be interested in these names where the meeting happened, Moscow, the Denisov, and what is the action going on, and so on. So in this big paragraph, there are certain points, certain words, and certain sentences which should be paid more attention in comparison to others. So this is the intention behind using the attention here. Attention is basically a way to pay more attention or to give more importance to certain sentences or words in the input over others, which can help in predicting the right output. For example, if we look here, now this attention can be temporally or spatially. When we talk about temporally, it means that, for example, there's a sentence, right? Now we are giving words, we're giving the sentence to the model, right? So at each time t, it is processing one word, right? Consider this example. So given these inputs x1, x2 up to xt, the hidden states are being processed, right? H1, H2, and so on. And then these hidden states will be serving as an input, one of the inputs to the decoder, which will be predicting the translation. So X is representing the sentence in the input language, and Y is representing the sentence in the target language, the same sentence. And the goal here is that this model should translate the sentence, give from one language to another language. And for that, the first step is to encode the input, which is being done here, and then use that encoded input to predict or to translate the sentence into the target language. Now here, if you look at these C1, C2, CTK, and CT and CK, these are nothing but context vector, which can help us in attending or paying attention to the important words or sentences if it is a long sequence of sentences, right? So in that case, how to create these content vectors. So for example, here the idea is very similar, that if we are predicting, suppose we are at time t and the word to be predicted is yt. This yt is depending on the current state of the decoder st as well as the previous state st-1, also at the same time the content vector t. Now if the input is too large, then the CT will be actually storing all these information about all these words equally. But what we can do is we can make CT pay attention, giving more weightage to certain aspects of the input, right? And that can be done based on how important that input is for the current state. So CT is defined as the linear weighted sum of the hidden states. And the weights are given by alpha t. So t is representing here that we are talking at some time stamp t. And alpha, the subscript j is representing the weight for the hidden state j corresponding to the jth token in the input. So CT is the weighted sum of these hidden states, and the weight of these hidden states is given using a softmax function over a score. So how to compute this score? So for example, when we are talking about CT, while computing the current state, it will depend on the previous state and the hidden states. And now we want these hidden states, the one which are very important to these current state should be given more weightage. So for that, we will use this score function. So the aim of the score function is that the words or the token or the hidden states which are more important in predicting the current word yt should be given more weight. And that can be like a simple score function can be just computing the dot product of the st-1 with each hidden states. So, and this can be one simple score function for it, right? And there can be many score functions, okay? And we will talk about those set of score functions as well. So the idea here is that, and this is what we are doing in temporal basis, right? So this is temporal attention here. So we are having a data, which is, so for example, at yt we are at time t we are predicting yt, at time t plus n we will be predicting yt plus n, and so on. So it's a temporal data, and how to give an attention here. The other possibility is that paying an attention to a spatial data. What I mean is spatial is, suppose there is an image, right? For example, in case of image captioning, the the goal is to generate a caption summarizing the image, okay, or the action happening in the image. And for that, the entire image may not be useful. Only certain aspects of the image has to be focused at a specific time t. So for that, we can use something called spatial attention. That is, now instead of taking the fully connected layer features here, you will be taking the output of this CNN layer. Why? The reason is that it will be maintaining the spatial information in the image. And now once we have these CNN features, we can then project back them into on this image, right? And this is how we can look at what these features. So if suppose the weight given to this specific yellow uh, yellow or this box is more, then we know that, okay, while predicting that word, the network was paying more attention to this region of the image. So this will also help you in explaining the model's output. But the main goal is that while predicting the words or the while predicting the output at any time t, the attention is paid to the corresponding image parts and not the entire image. Okay. So there can be multiple ways of scoring the similarities. So one is this content-based attention, in which you just compute the cosine similarity between the current state and the hidden state. Then there can be additive attention, in which score of st comma hi is equal to VAT into tan h of wa, and these w's or v's are the functions which are the values which can be learned using backpropagation. Similarly, for location based soft attention, you can multiply the state st with some weight and then take a softmax, so that will give you location based attention. However, the parameter w has to be learned during the training process. Similarly, we can have other score functions, and the score functions are not only limited to this. You can even explore other score functions, right? So the goal is all these score functions basically try to achieve the same aim, and the aim is that whatever is important in the input should be focused more. Let's talk about image captioning now in detail. So image captioning is the task in which we have to summarize the image. So suppose here is an image in which a person is wearing this hat, right? And let's say the caption to be generated is a straw hat. So the task is to identify what is present in the image, and one such answer is straw hat. So we get this image as an input to the CNN network. Okay, we got the output. Now, one thing is that because we are not doing the classification task, we are trying to predict the sequence of words which can describe this image content. We will use this fully connected layer features. So this is just before the classification layer. So taking the output of this fully connected layer and feeding it to the recurrent neural network as the initial at the initial phase. So initially, in case of RNNs, generally hidden state at time t was computed as weight like was depending on the current input x0 and the previous hidden state, right? This was what x0 is. This max represents the ReLU operation. Okay. Now, along with the current input x0, that is the words which are getting predicted, it will also depend on the features of the image represented here by v. And this w, all these w's has to be learned during training. And we are using this part, okay? And this is how things are going on. Now, once you start, if in case you want to have some kind of attention here, and you want to localize and pay more attention to each and every part of the image which are important to this word straw or head, then in that case we will not be using the FC layer output. The output will be coming from the convolutional layer because it will be having the spatial information which will be important. Now talking about image captioning with attention. So here, as I just mentioned, that in case you want to have attention, you want the CNN features because they maintain the spatial information, and it is easy to project these region of these features back onto the original image to see where that network is actually focusing right now. Okay, so suppose there is an image of dimension HW3, that is the height is H, the width is W, and it's a 3-channel image which is RGB image. And after applying, giving it as an input to the CNN network, we get the features of dimensionality L cross D. Okay. Now, what we will do? So the thing is that earlier here, if you see, we were just predicting the word. So for example, if we give the start token here, the word predicted is straw. Then we give straw as the token, and the word predicted is head. Then we give head as the input, and it will predict the word and token, right? Saying that okay, it has completed the captioning of the image. Now this sorry, what? Yes. So here we are using this FC layer output, right? This fully connected layer output, and this is good. This is good because this is summarizing the complete image for sure. But in case you want to have attention, because the image can be very complicated image, right? It can be a very cluttered image, and the task can be to summarize that image again. And in that case, you have to pay attention to certain specific regions of the image. So if you want to use attention, then taking these fully connected features may not be helpful. In that case, we will be going to the CNN features because the spatial information is not lost there. And that's what we are doing here. When we do image captioning with attention, we take the output of some convolutional layer of this network, and that will be serving as one of the inputs to the RNN model here. And now what will happen is that if you look at this RNN, it has some hidden state H0. It will also use these features, and at the same time, it will predict the attention. So this A is representing the attention corresponding to the word D1 to be predicted. Okay, so it will predict the attention A1, which will then be multiplied with this features map, and that will be given as an input to the next state. So this Z1 is nothing but the features, the weighted features, and the weights are being generated by the network itself. So these A are representing the attentions, the Z is basically A cross V. Okay, so this attended features will then be given as an input and the previous output, and that will be given as an input to this RNN model, which will then predict the attention for the next word as well as the next word it will predict, right? Once it has predicted D1, we will use this attention which is produced by it to produce the word D2. So this A2 times V, that will serve as Z2, Z2, the word which is predicted here using D1. So this is distribution over vocabulary, right? It can be a simple softmax layer, which is giving the probability of each word, and we select the maximum one. That word is Y2, let's say. So then for predicting the next word D2, it will be Z2, Y2, and H2, and it will be giving you A3, Y2, and so on. So in this way, this is also image captioning, but this is image captioning with attention. And when we are using attention, we are using the features of the convolutional layer and not of the fully connected layer because of the spatial information. So this is all about, so this is how we have seen the use of attention, both in sequence to sequence problems, as well as when we are doing handling images. Right? Now there is another concept which is very state-of-the-art models right now, transformers. And this is also used. So earlier it was introduced only for text, but now these days you will see a lot of models, a lot of applications in vision using transformers like image captioning, image classification, where transformers are playing a very an important role. So now there are something like vision transformers as well, and so on. So this transformer has mainly four components: the self-attention component, multi-head attention, yeah. So we have the self-attention, multi-head attention, position encoding, and encoder-decoder architecture. So these are the four components of the transformers. And now we will see each component in detail. Before moving on to that, let's just see how this transformer works. So the general flow is that you give an input to the model. So this set of encoders and decoders, this blue block here is representing the transformer model here. So giving an input to this input sentence to the model, it should produce the output sentence in a target language. So if this is our source language, then we want the output in a English. Okay. So from this JS is etudiant, it will produce the output I am a student. Okay. And this is the architecture. And now we will try to look and understand this architecture in detail. So starting with the first component, which is self-attention. Sorry. So, okay, before going to this part, self-attention, we will talk about positional encoding because this is how we first process the input. So, positional encoding is what? How to give the input to the transformer. So here, if you look at this transformer model, this is just a flow chart. This sentence cannot be fed directly to the encoder. So this sentence will be first embedded, right? We will get the embeddings of the words, and then we will also concatenate the positional encodings. So the positional encodings will be added to these word embeddings, and that will be serving as an input to the transformer model. Now, what is this positional encoding? The aim of the positional encoding is to capture the position of the word in the sentence. And for this, the this is how we compute the position encoding. So if the word is appearing at an even location, we will use a sine function. If the word is appearing at an odd location, we will use the cosine function. This POS is the position of the word, okay, and the word's position, and this is what it is, right? So this, okay, so basically what will happen is that we will have for each word, suppose there is an embedding of length 64. Okay, now how to get this embedding? So we have to add it, right? So suppose there is a batch of size 32 and each sequence is of length 10 and the embeddings are of dimension 500 cross 12, right? So what is this input shape will be 32 cross 10 cross 500. So similarly, we want this position encoding. So the position encodings will be also of the same shape, which is 32 cross 10 cross 512. And how we will compute the position encodings. So for that, what will happen is that this will depend on the word, position of the word in the sentence, as well as the dimension of its embedding. So for example, suppose we are computing the position of the fourth word in the sentence. So POS is representing 4, and this I will range from 0 to 5, from 1 to 512. So if the word embedding dimension is 512, then this I will be representing each and every index of that embedding, and that's how we will be computing it. Once we've computed these positional encodings, they will be added with the word embeddings and will be given as an input to the transformer. Now, the next component of the transformer is self-attention. What is self-attention? So suppose this X is representing here are these word embeddings. So for the first encoder, it will be word embeddings plus positional encodings. For rest of the encoders, it will be the output of the previous encoders. So suppose this X is representing the input to the module, okay? And these WQ, WK, and WV are the matrices which has to be learned by the network. Multiplying this W with X will give you the query vector. Multiplying the key matrix with the input will give you the key vector. Multiplying the value matrix with the input will result in the value vector. So corresponding to input X, we got the Q as the query vector, K as the key vector, v as the value vector by multiplying the input x with the matrices wq, wk, and wv respectively. Once we have done this, we will find the similarity. So we will do q into k transpose, and then we will divide this with the under root of the dimensionality of the key vector embeddings and apply a software. So that will give the weights over all these inputs, and that will be multiplied by this value vector to give you the final vector set. Now let's try to understand this procedure using an example here. So this is an example, okay, and there are two words. Suppose there are just two words, thinking and machines. So the embedding of the word thinking is x1, the embedding of the word machine is represented by x2. For now, assume this x1 and x2 has also taken into account the positional encodings here. Okay. Now we need to find these vectors q1, k1, and p1. So for each vector, for each input word x1, there will be a query vector q1, key vector k1, and value vector v1. How to get this q, k, v? That will be by simply multiplying this vector x with these matrices. Okay. Similarly, for the word machines, the same vector will be multiplied by these matrices wq, wk, wv to get the query vector q2, the key vector k2, and the value vector v2. So for the input, we have now computed the queries, the keys, and the values. Now the next step is, because it's a self-attention. So what does self-attention means? That in the given sentence, which words are actually important for a specific word, or the relation of the specific word with the other parts of the sentence. For example, consider a sentence: a cat is running on the road. Okay, so if you see the word cat, then cat is related to the word a. The cat is also doing the activity running. It is also going on the road. So all these words are related to cat, right? However, if you look at the word on, then on is playing an on is having more important, or its presence is important because of the word road, right? On depends on road. It's a proposition. So different words in the sentence will have different relations with other words of the sentences, and the idea here is to capture that information. So for each input, we have computed the query vector q, and now we will see how the other words are important or related with this word. Okay, so for that we will take the dot product of q with the key vector. So q1 dot k1, q1 dot k2, and so on. Okay, so this is the same expression we were doing here, right? Q into k transpose. Once we have done this q1, k1, q1, k2, and so on, we will divide it by the under root of the dimensionality of the key vector. So in case of transformers, it is 8 because here the length of the embeddings is 64. So dividing it by 8 will give you this value. And then apply the softmax over these inputs, 14 and 12. Finally, the probability will come 0.88 and 0.12. So one thing to note is that X1 has the maximum attention given to itself, X1, which makes sense, right? Because the word is very much important for itself. When you are talking about cat is very much related to its own, and the relation of the cat with, I mean, you understand it, right? So when you're paying, so this is the way we are weighting the attention which should be given to different words in the sentence with respect to this word. Okay, and it will be highest for the same word because of the statement, like because of the problem description here itself. Let us paying attention to the other words in the order of their importance. And using these as the weights, we will use this to compute the weighted average of the values. So it will result into v1, which is v1 is this vector, the v1 into 0.88 plus 0.12 times of v2, and that will give you the vector z1 corresponding to input x1. Similarly, the things will be done for x2 and so on. So this is how the self-attention is being done in transformer. The next thing we talked about is multi-head attention. So multi-head attention is the same thing as self-attention, but now repeating it for some m number of times. The idea is that if we do it for m number of times, then we will be able to capture more diverse informations which might have been missed if this operation was just repeated once. So now for each input, this like thinking machines, we will have these. So in case of transformers, it is generally this multi-head attention is basically 8 number of heads is 8. So we will have 8 set of these matrices, query, key, and value matrices. Each input will be multiplied with these set of matrices to get the corresponding query key vector value, which will then be merged together to get these values z0, z1, z7, and so on, and then which will be multiplied by some, which will be linearly multiplied by with this layer w to get the final vector z. Okay, so this is multi-head attention is nothing but the self-attention here, but now repeating it multiple times, and each head is representing one attention, so it is a multi-head, so it's like multiple times having the self-attention and then concatenating the output. The next step, the next component of this transformers is encoder. The role of encoder is to encode the input for further processing, and this is the architecture here. So whatever the input is given to this module, it will first go through the multi-head attention. The output of the multi-head attention will be added to the input here because of this skip connection and normalized. Then it will be given as an input to a feed forward network, which will then be again added to the input of the feed forward network and normalized. And that will become as an input to the next layer, which can be an encoder layer or a decoder layer. So in transformers, there are 6 encoder layers stacked on top of one another. And this is how it will look. So x1 is thinking, x2 is machines. Apply the positional embeddings, get this x1 and x2. Apply the self-attention, get z1 and z2. Now, then these layers are normalized. So it will be basically x plus z and this. So remember this layer normalized is coming from this add and norm, right? So the output is added to the input and normalized. And then it will be given as to this feed forward network, okay, z1 and z2, and then it will again be added and normalized. The next component is decoder. So decoder is also very similar to the encoders other than this part, right? Masked multi-head attention. Masked multi-head attention is important. So this multi-head attention is same. The only thing is masked. Masked is because it's decoding, right? Suppose there is a sentence you want to decode in Hindi, and the sentence is the cat is running on the road. And as we are predicting the sentence, that is Billy sadak par, okay? Now we do not want to pay attention to the words which are not yet predicted. So for that, we will use the masking here. So in this case, when we are paying the attention should only be distributed between the words Billy sadak par, not on the remaining future words which are yet to be predicted. Bhag rahi hai. So for that thing, we have this masked here. And rest of the architecture is very similar. So you apply the multi-head attention, you do that in normalization, and then it is very similar to it is exactly the same as the architecture of the encoder. This is also 6 layers of decoders are there. So it one over stacked over one over another, and so on. So any doubts so far? Any questions? Okay, then let's look at the implementation of transformers. Okay, so let's first look at this example, a very simple example. This is the state sentence, okay? Hello, I love you. And now there is this tokenization and embedding. Okay, so what does that mean? First, the sentence is being processed, and convert it into tokens. So the tokens here can be words: hello, I, love, and you. Okay, there is four tokens are created. You can further tokenize it depending on what tokenizer you are using, but for simplicity, let's understand that right now the sentence is be tokenized into individual words. Okay, so hello, I love you, and then we will be computing the embedding of each word. Okay, and those embeddings of each words will then be added with the positional encoding of the word and will be given as an input to the encoder module. Then the processing will be done here. Attention is there, so the query will be there, computing the similarity with different keys, which will be used to compute the softmax score, which will be then used to compute the weighted average of the values, and then it will be given as a relevant information about the entire sentence, which will then be given as an input to the decoder part. Decoder will take it and will start predicting the distribution over the probability, predicting distribution over the vocabulary to predict the most likely words, and so on. Okay? So if this is my input x equal to x1, x2, x3, x4, so these are the tokens. Each will be multiplied by the query matrix, key matrix, value matrix to get the query vector q, the key vector k, and the vector v. Okay. Once it is done, we have the query key and vector on which we will apply the tension. That is a softmax of q k transpose divided by the root of tk into v. The softmax of this, right? Softmax into v. And this will be the output of the attention network, right? Which will then be added and normalized, and then will be feed forwarded to the will be connected to the feed forward network, where it will again be added and normalized, and then it will be given as an input to the next layer. So let's try to start. So in this, we will now look at how to code this. So first is how to calculate the embeddings. So for that, we can use this PyTorch embedding layer, RNN.embedding. It will take two arguments. One is the size of the vocabulary, that is the number of words in the vocabulary, and the embedding dimension. Embedding dimension is the dimension of the embedding for each word. And this class embedding is just representing this embedding layer here. Okay, and this is already available in PyTorch. Then the next step is computing the positional encodings. So to compute the positional encoding, this formula we will use the sine and the cosine function. And how to do it? So the idea is that suppose these are the input words and this is their embedding vector. So we will have a matrix here where each row will be representing the embedding corresponding to that word. And so will be the size of the positional encoding matrix. That is, each row of this matrix will be representing the positional encoding of that word. And these two matrices will be added and will be given as an input to the first encoder of the transformer. How to implement it? It's quite easy. So we will just follow this diagram here. What we will do is, this embedding dimension is the dimension of the, what is this embedding dimension? This, the size of the number of columns in this matrix, right? So in case of transformers, it's 512. Okay, then once we have done this, we now need to compute this position encoding. So we know the size of the embeddings and the positions. So positions is basically the maximum sequence length, which means that any sentence in the input will not be greater than this length. So for that, we will have this max sequence length here as the number of rows. So a zero matrix has been created here with number of rows equal to the maximum length of the sentence and self dot embedding dimension representing the embedding size for each token of the input. Now for position, now the next step is to compute the positional encoding using this formula. So for that, what we will do, so this POS is representing the POS in the numerator, and this I will be represented by the second loop here. So computing the positional encoding of the word at position POS, and for the ith index of its embedding, the formula will be this. Okay, and for even it will be sine, for odd positions it will be cosine. So this is how the positional encoding has been created. Note that this has been unsqueezed here because of the batch size. So there was no batch dimension here. So it will now of the shape of 1, comma, maximum sequence length, comma, the embedding size. Okay. And then whenever an input will be given to it, it will take the input, right? It will multiply it with the square root of the self-dot embedding dimensions, and then the sequence length will be computed, and then it will add the x with this positional encodings here, okay, and return. So now this has computed. So we have computed the embedding here, class embedding, and the positional encodings, and added the positional embedding to the word embedding. The next step is to write the self-attention. Okay, so how to do that? So now we have the embedding dimension and the number of heads. Okay, so in transformer we have 8 heads, and the dimensionality of each head will be then dividing this 512 dimensionality into dividing by 8. So that will become 512 cross divided by 8 equal to 64. That will be the dimensionality of each head. And then apply the query matrix, key matrix, and the value matrix, right? So for that, this is implemented as the linear layers, whose input will be of these single head dimension, and the output will also be the single head dimension, right? So these query, so what will be the dimension of the query matrix here? The dimension of the query, key, and the value matrix is 64 cross 64. And there is another linear layer in this. So remember the architecture for the attention. Okay, it's not. So it was in the slides. So the once we have these inputs, this query, key, value, and we have computed the weighted average of the value, the output was concatenated, right? So that's why we have another linear layer which will be taking the concatenated output, and then and the output will be the same shape as the embedding dimensions. So for multi-head attentions, whatever the input is given, which will be having this key, query, values here, computing the key, which is key dot view. So this is just to reshape it. Okay, so this is important, like how the processing is being done here. So suppose says the batch size of the we are talking is 32. Okay, and each sentence has 10 tokens. So it's a sequence of length 10, maximum length 10. And for each token, the embedding is of size 512. So this is 32 cross 10 cross 512. Now, in case of multi-head attention, this 512 can be represented as 8 into 64. So reshaping it, it will become 32 cross 10 cross 8 cross 64. Right? Now, once this becomes, okay, I think we can look here. Okay, so we have this 32 cross 10 cross 8 cross 64. Now we can reshape it to so that we can process for each head independently. So it will become 32 cross 8 cross 10 cross 64. So transpose it and it will become this. Okay, so this is our input, and our query matrix will be multiplied by this input to give you an output, and same will be with the key matrix and the value matrix to give you the query, key, and value pairs here. Okay, so here coming back to this, the thing will be We will apply the key matrix over the key to get the k vector, query matrix over the query vector to get the q, and value matrix over the input value to get the v. So once we have this q, k, v, the next step is to compute the similarity of the query with the key. Okay, so for that, q and k are being multiplied. And then next step is dividing it by the square root of the dimensionality. And then after division, apply the softmax function. And using this scores, take the weighted average of all these values. And that will give you Z1. That is the output corresponding to the input here, right? And then once it is done, pass it through this fully connected layer here, self.out of concat. Remember this layer? And that will be the output of this multi-head attention. Now, so to implement this encoder, we have already done this multi-head attention. Then what is left is this entire architecture, which will be now comprising of this multi-head attention. We have already seen add a norm layer and feed forward layer. So for that, the architecture of the transformer encoder is very simple. So first, let's see what this transformer block is. We need an attention and the normalizations and a feed forward layer. And the forward pass will be very simple. Whatever the input is coming, key query value, give it to an attention, get the output. To that output, add the input itself, which was value. So attention out plus value. So this is addition. The next is normalization. And then apply the normalization to it. Once this is done, give it as an input to the fully connected layer. So feed forward layer. Add to the output, add the input. So it will be feed forward out plus norm1 out. The next step is normalizing it. So normalize the feed forward residual out. And this will be the output. So this is simple transformer block. And what will be the encoder? Encoder is nothing but this. So this is one encoder block, right? However, in case of transformer encoder, there is a layer of these modules. So for that, final transformer encoder will be, we need an embedding layer, a positional encoding layer, and multiple encoder layers, right? Which is being represented by this class transformer block. And the forward pass will be very simple. Whatever is the input, embed it, add the positional encoding, and give it as an input to the encoder. So this out is representing the output of the encoder module of the transformer. The next is decoder. So decoder is also follows the same structure here, right? Take the input from the encoder. But before that, whatever the words have been predicted so far, the output embedding, so output is coming from here, right? So whatever is the output embedding, apply the multi-head attention over those output embeddings as well, and take the output of the encoder and then follow the same encoder structure. So decoder is very simple here. For decoder block, we need an attention, a normalization, a dropout, and this transformer block is nothing but the encoder, right? And this encoder is this part of the network. Okay, so attention, normalization, and this encoder part. Attention, normalization, and this encoder part. Dropout is added as a regularizer here. So if we have a fully connected layers, then we add dropout, in which during training, randomly each neuron is dropped with the probability, dropout probability, okay? And during testing, the adjustments are made by using that P probability while taking the output from the network. So that decoder block architecture is that we have this attention network, the normalization, the dropout, and the same as the encoder block. So for forward, whatever the input is coming, apply the attention onto it and a mask. So this mask is important here, and it is only in decoder. The reason is that we do not want to give attention to the words which are not yet predicted by the decoder. So this mask is only for the words which have been predicted so far. And that's why we are using masking. And then we have this value. This is during training part, by the way. Okay. Value, self.dropout, and output is self.transformer block. So finally, transformer decoder is nothing but multiple layers of this decoder block, right? So the transformer decoder block is this. We need the word embedding and the position embedding. This is for the output embedding, the outputs which has been predicted by the decoder module so far. And a layer of these decoders. And then finally this output layer. So here it will be. So this output layer is to compute the softmax probability. Right? So finally what will happen is take the word embeddings, get the positional embeddings, add the dropout as a regularizer, then take the encoder output, this X and the mask, and give it as an input to the decoder. Okay, so this is the decoder. Remember, this decoder is here, which takes this key, query, X and mask. So the same thing is given here. Key, query, X and mask. Okay. And with this, whatever is coming, just apply the software to get the distribution over the words, and the most likely word will be predicted. So the complete transformer in a nutshell is you need to have the target vocabulary size. The encoder, we already saw this transformer encoder module. For decoder, we already saw the transformer decoder. So what will happen is that whatever the input is given, the source sentence is given to you, create a mask. So why we need this mask? This will be required during the training of the decoder. So for the target sentence, the mask is created as this. So for the first time step, only the first word will be important. The one word it is going to predict. For the second time step, for the first word, there is no attention which we can give to any words because that is the first word which is going to be predicted. For the second word, the attention can be given to the word which has been predicted already. That is the first word. While predicting the third word, the attention can only be given to the first two words which has been predicted and so on. So for that, we will use this lower triangular matrix as a mask here. And so create a mask, get the output from the encoder and get the output from the decoder by passing this output from the encoder, the mask and the target sentence, because that will be used. Why it will be used? Because it will be used here. So let me go to the decoder here. Yep. So if you see here, we have this X, comma, encoding out, comma, mask, right? So for that, we are passing here. And once we have this, get the outputs and it will return the output. And what are the outputs? Outputs are nothing but the final target sentence, which is being predicted. Okay. So here's a model. So testing this code. Okay, and this is the entire model being printed. You can look at it. The notebook will be shared. And then during inference time, this is like if the torch tensor is this and the target tensor is this initial tensor, and then it will decode it and it will predict output. Okay, so here this is a numeric form because the vocabulary has been created and each has been assigned. So each value here is representing the index of the corresponding word. Okay, so with this, the tutorial on transformer, so we can stop here now and we can take the questions.